This is an intro. This is an intro to my calculus video. This is an intro. I have to sing it myself because I don't like ads. So today's lesson is going to be about finding volumes, but finding volumes by rotation. So take for instance this small region I have defined by a line and two edges. If I were to rotate that region around the x-axis, I get this sort of piece of a cone. Now, how do we find the volume of this? Well, let's look at a particular slice, this blue slice, and this blue slice has a thickness and it has a height. That thickness is dx and the height is r. Now if you were to look at this from the front view, you can see that this slice is actually a circular disc. So it's kind of like a really thin cylinder with a height of dx and a radius of r. So finding the volume of a single disk is a matter of multiplying pi times the radius squared and dx, which is the width. We can use an integral to add all these disks up. So if I were to have these other disks, and obviously we want to make dx as small as possible, that gives us the most accurate amount of volume, then we can get a formula for the volume of this as pi times the integral from a to b of r squared over dx. So let's look at an example. Let's take the function y equals the square root of x, which looks kind of like this, and let's examine this on the interval from 0 to 1. So I get a region here. Let me just get the right color. And we want to rotate this region about the x-axis. So as I rotate this, you'll notice that I kind of get a mirror image on the other side of the axis. And then it's circular around its edges. So this is sort of the tip of a bullet kind of a shape. And like we did in the previous example, I'm going to look at a specific slice. This is going to help me to identify the radius and where that radius is coming from. So here I'm looking directly at the x-axis and the y-axis is moving up and down. And that radius, the distance from the axis of rotation, the x-axis, is equal to the height of the curved function, which was y equals the square root of x. So what I want is actually the y-coordinate, which is equal to the square root of whatever value of x I happen to be at. So the volume of this solid is pi times the integral from 0 to 1 of r squared, or the square root of x squared dx. And solving this, we get pi over 2. So now let's take a look at something a little bit different. A new function, y equals x cubed, bounded by y equals 0 and y equals 8. So we'll draw a picture. Y and x-axis, y cubed or x cubed, and then y equals 0 is just the x-axis, and y equals 8 is the line. And again, when we rotate this around the y-axis, we're going to get sort of cylindrical discs, and again another sort of bullet shaped solid. And we're going to look at one specific slice. I'm kind of highlighting it here this time. Now remember that these discs, we're ultimately, by using an integral, making their width infinitesimally small. That's why we use the differential to define the width. So r, we want to be represented by the distance from the y-axis out to the curve. So the distance from the y-axis out to the curve is actually the x coordinate. So we'll have to solve for x. So r is equal to the cube root of y. And plugging that into my formula, my volume comes out to be the integral from 0 to 8 of y to the 2/3 dy, which is 3 pi over 5 times 32. So while I clean up my workspace here and get ready for the next example, I just wanted to go back and make sure that we understand that we're cutting this solid into thin slices. Each of these slices has a width of some differential. And in that last example, the differential was dy because the width was in the y direction. And my slices were perpendicular to the y-axis. And the same thing goes for the example before that, where my differential was dx. But in that one, my slices were perpendicular to the x-axis. So in the last two examples, we saw a region rotated around an axis of rotation, and it created a solid whose cross sections looked like circular discs. So in both of those examples, the region was on or adjacent to the axis of rotation. But what happens if we moved my region, say, away from my axis of rotation, like we see here? So I have this rectangular region, it's off the x-axis, and when I rotate it about the x-axis, I get sort of this thick washer type solid with kind of a hole in it. And that's exactly what it is. It's a washer. So the cross sections of this are going to look like two cylinders, one cylinder and a smaller cylinder that's been subtracted from it, a smaller cylinder with a smaller radius. So for the volume of each of these disks, we're going to have pi times the integral from a to b of large R squared minus small r squared. So let's look at an example. So let's take the functions y equals x and y equals x squared on the interval from 0 to 1. Let's get a picture going. Y equals x squared, y equals x. Now, if I rotate this around the x-axis, you can see that on the interval from 0 to 1, the region isn't always touching the axis of rotation. So again, I'm going to mirror my region and then draw my circular edges. You can sort of see now that this is like a cone, but with sort of a trumpet flute that's been taken out of the center. So if I were to slice this and take one of those slices out, it's going to look circular, it's going to look cylindrical, but it's got a hole in the middle. So let's look at this red disc here, or washer in this case. Okay. So this red washer has a hole in it. Okay. And so now I need to figure out what my R's are, what my small radius and what my large radius is. So my small radius is the distance from the x-axis to the inner part of this disk, which is going to be the smaller of the two functions, the function that's closest to the axis of rotation, and in this case it's x squared. And the large radius, again, from the axis of rotation up to the outermost edge of the disk, which in this case is going to be the function y equals x. So using my formula, the volume is equal to pi times the integral from 0 to 1 of large R squared minus small r squared. And we get something like pi times 1/3 minus 1/5, which is perfectly simplified if you ask me. Okay, so now let's look at something that kind of introduces two new ideas. So the first one being an axis of rotation that is not the x or y axis. So we're going to actually use the same functions, so we have the same region. However, this time we're going to rotate around the line x equals -1. So as you can see, the axis of rotation, again, it's still off of the region, so I'm going to have a hole, or this large gap on the interior. And this is sort of a bowl shape. It's roundish on the outsides, but it's conical on the interior, but it wouldn't actually make a good cereal bowl because there's a hole in the bottom of it. That is because no part of the region is touching the axis. So here's a disc. It's rather large, and it has that width in this case, which is a dy. Let me go mark that on the last problem. In this case, it's a dy, and the distance from the axis of rotation to the inner part of that ring is the distance 1 back to the y-axis, and then from the y-axis to the line, which is the x direction. So that's going to be 1 plus y. And large r is going to be the distance from the axis of rotation to the outermost edge of that ring, which in this case is going to be 1. That gets me back to the y-axis, plus the square root of y, which is the x coordinate of the outer curve of the original region. So plugging this into my formula, volume equals pi times the integral from 0 to 1 of large r squared minus small r squared. We get something like pi over 2. Thanks for watching. Thanks for watching my calculus video. Plus, see you next time.